All right, we're starting our last chapter of first semester, making sure we understand what's going on. Let g be a continuous function on this interval from 0 to 1. Great. Which of these following is not necessarily true? We went ahead and graphed that out. A very basic graph, but we graphed it nonetheless. This is a great representation because it's just kind of weird, and we got to think our way through it. There exists a number on the interval from 0 to 1 such that g of h is greater than or equal to g of x for all x values. That one right there is just weird to say, okay? Here are 2 points that I know. In your mind, draw a line that connects those 2 points. You got it? Is there some place on that graph where the y value is bigger than or equal to all of the other y values? Yeah. Like, think about what that means. If I connect these 2 dots right there, is there a y value that's bigger than the rest? Yeah, that spot right there. Okay. Oh, let's do this instead. Whee. Oh, yeah, right there. Okay. Let's say I did this instead. Doop, boop, 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 boop. Yeah, that one's the highest still. Okay. We could do lots of different things. But it basically says there has to be at least some maximum on this closed interval. That is true. Okay. This is an extreme value theorem. That's what we're going to learn tomorrow, but you just did it. It's really obvious. You got to have a point that's higher than everything else. Okay. So that one has to be true with what we're doing. Letter B, I had to read it like twice last period because it just looks weird. For all A and B on the interval, if A is equal to B, then G of A is equal to G of B, which is the dumbest thing I've ever heard, but it's this. If you have 2 numbers that are the same, pick 2 numbers in between 0 and 1, a half and a half. If 1/2 equals 1/2, is G of 1/2 going to be equal to G of 1/2? Yeah, that's so dumb, but it's true, right? I have no idea why in the world they would do that besides the fact to make your brain hurt more than it needs to. But that one works. Okay, so B is true. There exists a number from 0 to 1 such that G of H is equal to a half. What is G of H representing here? It's the Y value. Is the Y value going to be equal to 1/2 somewhere on that interval? Yeah, somehow there's no way that I can get from here to there without going through that because we are continuous. It has to be true. We talked about that before. Anybody remember why that's true? Yeah, that is IVT. Good. That is intermediate value theorem. Remember intermediate value theorem? That was if you, at 2 years old you were 2 feet tall, and at 18 years you're 6 feet tall. Were you ever 4 feet tall? Yeah, as long as you were continuous, you have to hit every number in between. That is what C is as well, so that one's good. There exists a number such that G of H is going to be equal to 3 halves. Do I have to go through 3 halves right here? Nope. I just draw that line right there and I wouldn't go through it. So no, that one's the one that does not have to be true. What about the last one? It says, for all H on this interval, the limit of G needs to be equal to G of H. Does that have to be true? It does, because we said this is the one that doesn't have to be true. D is the answer, but that means E has to be true. Talk with your neighbor and explain that concept. What does that describing and what does it mean? So this last thing is the definition of continuity. Okay, remember what continuity is. Continuous lines. In order to be continuous, 3 things need to be true. The limit from the left, the limit from the right, and the value all need, and the middle need to all be equal to each other. Left, middle, right. Okay. This is the other definition that the limit has to exist, a value has to exist, and the limit needs to be equal to the value. This is just continuity, and we know that it's going to be true because it says it's continuous. That's why we're going to review in a couple weeks. Just keep building as we go. All right, today we are talking about mean. All right, today we are talking about mean value theorem. This is a really important theorem that we're going to understand. And the whole idea with mean value theorem is this. Let's talk about the mean police theorem in terms of, has anyone ever gotten a speeding ticket before? Yeah, you got a speeding ticket. How fast were you going? 85 and a 60. Not great. Not great. So were they right to pull you over? Yeah. Oh, don't ever speed in Ohio. Speeding in Ohio is guaranteed to get you a ticket. Let's think about this real quick. Okay. Woo. That's pretty solid. That's a good police car right there. Okay. There's my police car. Anybody been on a toll road before? Oh, on a toll road. All right. So let's talk about a toll road. A toll road is just is like a road that is a little bit less traffic because you have to pay money for it, all those different things. Let's say you were driving on this road. You got your little car here. Apparently, it's a strange looking car, but that's my car. Okay. You see this police officer right there. So you're like, oh, not getting a ticket today. No, sir. The speed limit is 75 miles per hour. And you go right by that guy at 70. You're nice and good. He's not going to look at you because you're going too slow. You're going the right speed. You're happy about what's going on. Okay. Then you travel 100 miles. It's a long toll road. I'm sorry. Yeah, 100 miles. It took 1 hour to travel that 100 miles. And then you see another police car here at the end. And right before you get to that police car, you're like, not today. I'm going to go 70 miles an hour and just cruise on right by. And you go 70 miles per hour and you cruise on right by. And then he pulls you over and gives you a ticket. Was he right to give you a ticket? Were you speeding at some point during that trip? Yeah, by a lot is the right answer. Yeah, I know. You hope that police officers don't get better at math. We're in trouble here. Yeah, you're speeding. How do we know that we're speeding there? How do they know that? I traveled 100 miles in 1 hour. So on average, what was my average speed during that time period? 100 miles per hour. He only saw you going 70, so you're like, oh, I'm good. Were you ever going above 75 miles an hour? Yeah. Were you ever going over 80 miles an hour? Over 90? Over 100? Yeah, Alana, you're saying you're definitely going over 100. How do you know you're definitely going over 100? Yeah, we got to make up for that ground when we were cruising along going 70. So at some point, you were going like 100 and something at least. Okay, so you rightfully got that ticket. But that's mean value theorem. That description of what I just gave you is exactly what mean value theorem is. Your average speed during that time period is 100 miles per hour. At least once during that trip, you had to be going 100 miles an hour. Okay? Your average speed has to be equal to your instantaneous speed, meaning at some point when you look down at your speedometer, there was at least one point where you were going 100 miles an hour. Okay? You might have jumped all the way up to 180 and then came back down, and for most of the time you were good. But at least once, and in this case, 2 times, because there's no way to go from 70 to 70 without hitting 100 in there. Twice, you had to at least be going that. Kind of makes sense, the description. Your average has to be equal to your instantaneous at least once. All right, let's talk about it a little bit more mathematically then. Mean value theorem says that somewhere between points A and B on the differentiable curve, there's at least one tangent line parallel to the secant line. That's a lot of math talk. Let me show you visually what that means. You got 2 points. Okay, that's my time interval. So on this time interval, from here to here, during that time period, your slope is this line right here. This is my secant line. That's my slope. That's the average between that time period. That's my average rate of change. Mean value theorem says that if you are differentiable, your average rate of change is going to be equal to your instantaneous rate of change, your tangent line at one point. There's at least one place where those slopes are the same. Okay, no matter how you draw a graph, let's just make up a new graph. Okay, so here, that's ugly. There's a graph. This is my average slope. Is there somewhere on that graph where my average slope is equal to my instantaneous slope, equal to my tangent line? How many times? At least twice, right? Because if its slope is that, like probably right about here, my slope is that. Oh, just kidding. Like right about there, my slope would be that. And right about here, my slope would be that. Okay? I didn't draw it very well, but my slope has to be equal to that. What about this? Think about an absolute value graph. The slope here, if I did the slope here, my slope is that. Is there anywhere on this time period where my slope is going to be equal to that same slope, where my tangent line is going to be equal to that other line? The answer is no, right? What your slope is going to be this. Your slope is -1, and then your slope changes to +1. Is my slope ever 0? What's the slope right here? Undefined. And so that's why when we do mean value theorem, we have to be differentiable. Okay, mean value theorem, you have to be differentiable, or otherwise it doesn't work. Let's read the definition again. It says if f is continuous at every point on a closed interval and differentiable at every point on the interior interval. So all of this, it gets a little complex. All you really need to get out of that is you are differentiable on an interval. If you are differentiable on an interval, then there's at least some point C. Okay, so there's at least some time where this is true, that the instantaneous rate of change, that the derivative is going to be equal to the average rate of change. Okay, so if a differentiable interval, then the instantaneous rate of change. What's another word? I keep using the phrase instantaneous rate of change. What's another word for instantaneous rate of change? Then the derivative. Then the derivative has to be equal to the average rate of change. What does the average rate of change mean? The slope. The derivative has to be equal to the 2-point slope on that interval. The instantaneous rate of change has to be equal to the average rate of change. That's the idea. All right. All we're going to do today is explain that in more detail and get you better at that. Average rate of change is going to be equal to the instantaneous rate of change. Question so far? Let's do it. Okay. It says explain why there must be a value for C from 1 to 3 such that f prime of C is equal to 4. Okay. When you read this question, explain why there must. Anytime you read that, it is a theorem question. It is either instantaneous, or I'm sorry, it's either intermediate value theorem or mean value theorem. This is a mean value theorem question, and I know that because it's talking about derivatives. When you're talking about derivatives, that is mean value. Mean. What word do you think about in math class when you hear the word mean? Average, right? Mean. When you hear that word mean, oh, that's average rate of change. Oh, okay, it's a slope question. Okay, so here's what we're going to say. Explain why there must be that true. So if this has to be true, I'm thinking MVT. And MVT does average rate of change. So the first thing I got to do is find some endpoints, just like we did with IVT. We got to find some endpoints. So we're going to find f of 1 and f of 3. I'm doing it for this equation right here, which is just x squared. What is f of 1 going to get me? 1. What is f of 3 going to get me? 9. I just plugged in. Okay. Then I'm going to find average rate of change. How do you find the average rate of change? Yeah, just slope. 9 minus 1, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That gets me 8 over 2. My answer is 4. That is my average rate of change. Once I've found that, I've answered my question. Okay, I need to put that into some words so that we make sure we're clear on that, but that is my answer. Okay, so now we're just going to write our answer. This is not like IVT where you had to have 5 things. Okay, there's really 2 things you got to say. Okay, so here's what we're going to say. On the interval. I'm just going to say on the interval from 1 to 3, f of x is differentiable. I have to say differentiable because I'm talking about derivatives. This is a derivative question, so I have to talk about differentiable. Is x squared differentiable? Yeah, we know that. It's a polynomial. You can take the derivative of polynomials. You don't need to say why, but it is differentiable. On the interval 1 to 3, f of x is differentiable. And the average rate of change is 4. So by MVT, and then there's going to be some writing, but all this writing is just me saying, yeah, I'm good. So by MVT, then I'm going to just restate this. That phrase right there. By MVT, there must be a C on, there must be a C for 1 is less than C is less than 3, such that f prime of C is equal to 4. So as long as you're differentiable, your average rate of change has to be equal to your instantaneous rate of change by mean value theorem. Okay, so we said on my interval, I'm differentiable. I stated the average rate of change. Not only do you have to state it, but you have to show it. This is part of my answer, showing that I did the average rate of change somewhere. Okay, and then just say, hey, by MVT, that has to be true, and I just restated the sentence. Kind of makes sense where I'm getting all that from? So visually understand what we just did. We said from 1 to 3, this is the average rate of change. That's the average rate of change. Is there somewhere on that curve from 1 to 3 where the slope is going to be the same as that line? Yeah, we think so. But let's find out where. So we did part A. Okay, we explained that. Part B says find the value for C that satisfies MVT. Okay, so we want to prove what we're saying with that is we're proving this. F prime of C is equal to 4. So what's F prime? Yeah, it's the slope. What's F prime going to be if it's x squared? 2x. The derivative of that is 2. I'm taking the derivative of x squared. Oh, that's 2x. And I want to know when is the instantaneous, the derivative, equal to 4? When x is equal to 2. If I go to this graph, when x is equal to 2 right there, oh yeah, the tangent line would be equal to the average rate of change. That is the place where we're looking for. That is this mystery C value where the derivative is equal to the average rate of change. Questions there? Does mean value theorem, I'm saying it doesn't work for this equation right here. I kind of already said it. Why is mean value theorem not going to work for that, Luke? It is not differentiable. On this interval from -1 to 1, it's not differentiable. Okay, because think about what that graph is. From -1 to 1, boom to boom, not differentiable. What if they said from like 1 to 2? Would mean value theorem work? Yeah, because it's differentiable. It's just a line. But in between there's a corner point, and I can't do mean value theorem. Let's go to the backside. Example 3, they gave me an equation. My job is to find the C value on this interval that satisfies mean value theorem. So I'm trying to find the C value. That's exactly what we just did right there. Okay? That's what we did. And so what you're trying to do is figure out when is the derivative equal to the average rate of change. Do that with your neighbor. Go. We start off on this problem. Jesse, what do you start off by doing here if I want to prove MVT? I got to find the slope. And so to find the slope, you got to find some ordered pairs. I got to figure out what the endpoints are because I got to find the slope between 2 points. When you plugged in 0, Jesse, what'd you get? -1. And when you plugged in 1? 2. Okay, cool. So we've got those points real quick. Then we're going to find the slope. So if we're finding slope here, it's y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. So minus a negative, I get 2. That is my average rate of change. That's 3, guys. Why would you say 2? That's ridiculous. 2 plus 1 is definitely 3. No one would do something that silly, but it's 3. Okay? Once we've got that, we want to know when the derivative is equal to that. So I got to find f prime of x. So Cannon, what's f prime of x going to be? 3x squared plus 2. That's his derivative. He's going to figure out when that derivative is equal to 3. Yes, ma'am. Lulu, you got a question? Okay. We want to figure out when the derivative is equal to 3. Average rate of change is equal to the instantaneous rate of change. We set them equal to each other, we're going to solve. So 3x squared is 1. Divide by 3, divide by 3. X squared is 1/3. We square root. X is going to be equal to plus or minus the square root of 1/3. Kind of. That's not my answer. Only one of those is what we want. Why is it plus, Jesse? Because I am on the interval. I only want answers on this interval. So since my interval is 0 to 1, I only want the positive version. Questions there? The hardest thing about mean value theorem is just understanding when to apply it. When you realize that I'm applying it when I'm trying to find the derivative, it's pretty straightforward. Use intermediate value theorem to show that the function has a 0 on this interval from 0 to 1. Use your brain. Think back. Talk to your neighbor. You're going to need to do this in a couple weeks anyway, so remind yourself how to do that. Go. How we can do here. Max, what's something you put? Buy IVT. We're not going to be in the best order of all time, but we're going to get all 5 parts. So buy IVT. Love it. Taylor, what else did you put? On the interval. From 0 to 1. Cool, we need that too. We're going in a strange way, but I enjoy it. We're going to get there eventually. Andrew, what else do you need? All right, we got some other ones in there. So continuous. By IVT on the interval from 0 to 1. Since f of x is continuous. All right, there's my third thing. So IVT interval continuous. 2 left. Endpoints. And so since f of x is continuous and f of 0 is -1 and f of 1 is 2. So we said the endpoints. Then we can just wrap this thing up. Okay. There must be a 0 because, and we're just stating the endpoints, f of 0 is less than 0 is less than f of 1. So we said IVT, the interval, continuous. We talked about what the endpoints actually were. This, and then we said that 0 falls in between them. Oh, super ugly. That was the worst constructed one ever, but we're getting full credit because I got all 5 elements of it in there. Questions on that one? That's just a reminder. That's not necessarily what we're doing today, but that's okay. Let's go to example 4. Let f be a twice differentiable function such that f of 2 is 5 and f of 5 is 2. Explain why there must. As soon as you read that phrase, explain why there must, you're thinking, all right, this is a theorem question. That's the only way we ever explain why there must. It's a theorem question. Okay, it's either IVT or MVT. It's MVT. Okay, and you can tell that because it's f prime of c. It's it's the derivative of something. Write your answer. Give me a justification to this thing. Give me an answer that would get you full credit on the AP exam. Talk to your neighbor. Do it. Go. Here we go. So we're explaining why this must be true. This is a mean value theorem question. So if I'm doing mean value theorem, Lulu, what do you got to do here? You got to show my work to find what? The average rate of change. We've got 2 endpoints. So the first thing we're going to do is find our average rate of change. Okay, so she's going to show her work. You have to show it. She's exactly right there. So y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I get negative 3 over 3. I get negative 1 as my average rate of change. Okay, once I've gotten that, then I can answer my question. So I'm going to say, since f of x is, what it has to be true if I'm talking about mean value theorem? It has to be what? It has to be differentiable. Since f of x is differentiable on 2 to 5, and the average rate of change is negative 1. And I have to show my work, otherwise I can't say that. Is negative 1 by MVT, and I'm just going to super cheat here, but they would let you do this. By MVT, that must be true. And I'm going through this. All I would have to do is just restate that. So I'm just saying by MVT, that must be true. I'm saying everything I need to. Make sense on what we're doing? Again, really, more than anything else, mean value theorem is, are you differentiable? Cool. Then your average rate of change has to be equal to your instantaneous rate of change. I'm done. Look at number 5. Just real quick, last one. The table gives selected values of this continuous function. Can we use mean value theorem to say that g prime of x is equal to 1/2 on this interval from 100 to 101? Talk with your neighbor. Come up with a yes or a no. I'll give you about 60 seconds. So if I'm trying to use mean value theorem, I found the average rate of change. I already did that work for you. G of 100 is that. G of 101 is that. I did slope. I got 1/2. So since I got slope of 1/2, does mean value theorem work here? No. We can't necessarily use mean value theorem here. In theory, it works, but why can I not apply it here? Jesse? It says continuous, okay, and it's not saying that it's differentiable. It could work. If it is differentiable, then absolutely it's going to work, okay? But if they don't say it's differentiable, then I don't know if it's going to work or not. It has to be differentiable in order to apply mean value theorem. Kind of makes sense what we're doing today? Yeah, if I said differentiable, then you know it's continuous. But just because I'm continuous, it doesn't mean I'm differentiable. Great thought. You